So now we're going to talk about the resonance energy. So what is the resonance energy? It is the energy difference between most stable resonating structure and resonance hybrid is known as resonance energy. Most stable resonating structure and resonance hybrid is known as resonance energy. Now we have qualitative aspect, qualitative aspect. Second we have quantitative aspect. Qualitative aspect and quantitative aspect. Let's talk about first quantitative aspect. How do we quantify the value of resonance energy? Quantitative. How do we calculate the value of resonance energy? That is quantitative aspect. So, what is quantitative aspect? The difference in the experimental and calculated energies. Which type of energies would be there? Mostly will be heat of hydrogenation. What is the heat of hydrogenation? That will be calculating for one compound by which we will be observing the one example through which we will be understanding by which compound is stable. How much by energy the compound is more stable is known as resonance energy. So how much compound is stable is known as resonance energy. Higher the value of resonance energy, greater will be the stability. So how do we calculate the resonance energy? Like first of all, the most common example, resonance energy of benzene. Let's calculate resonance energy for the benzene. Now resonance energy in benzene we are calculating with taking the respect of heat of hydrogenation. Like we have one cyclohexene, when we hydrogenated it, it formed cyclohexane and releases 28.6 kilocalorie heat. But when benzene is treated with hydrogen 3 moles, it should be forming cyclohexane for 3 times 28.6 kilocalorie. That value should be 85.8 kilocalorie. But the value was the observed value, or we can say experimental value. Experimental value is 49.8 kilocalorie. So resonance energy is calculated value. How much value we have calculated? And observed value must be less from that observed value. That must be less than to it. How? Calculated value minus experimental value, not observed value. We can say it as an experimental value. So calculated value was 85.8 and experimental was very less. So then 36 kilocalorie is the resonance energy. Means let's understand by conceptual that this bond required to make and releases 28.6 kilocalorie. So this bond should require 3 times energy. But actually there is more stability, means energy less. The overall energy is less of this molecule because the resonance. And that lesser value we calculated by subtracting in the experimental value, calculated value with the experimental value. That's how we calculate the experimental value. So that's for the qualitative aspect, quantitative aspect. Now let's talk about the qualitative aspect, which is quite important. qualitative aspect. Qualitative aspect, if we talk about, so first of all we have CH3 C double bond O negative, that is in resonance with CH3 C O negative double bond O, and its resonance hybrid is CH3 C O and O delta negative, and it is the partial double bond. So we talk about energy. It's A, it's B, and it's C. So A and B are equal energy because they are equally contributing. Then we have C. So the energy difference between A, B, and C is known as resonance energy. So delta E, EC minus EA. So this is the most stable canonical structure. A and B both are equally stable, and C is the resonance hybrid. So as we have seen the definition, the energy difference between most stable resonating structure and resonance hybrid is known as resonance energy. Now, if they are not equally contributing, let's talk about CH2 minus C double bond OH, and its resonance is CH2 double bond CO minus H. So it is CH2 COH. Here we have delta negative, and here we have delta negative. So C, D, and E, if we talk about C, D, and E, the energy difference between D and E and C and E, which is this is the resonance energy, because D is the most stable. How D is stable? We know that the negative charge on the more electronegative is more stable. We have seen already in case of the stability of resonating structure. So delta E, resonance energy, will be E D minus E E. E D minus EE. So this is the value of resonance energy, most stable structure and the canonical form, and the resonance hybrid is known as resonance energy. So how do we calculate the order of resonance energy? But every time we are not able to draw the diagram. So first rule is aromatic has the highest resonance energy, then non-aromatic, then anti-aromatic. This is the order of resonance energy. So if we talk about, this is the aromatic compound and this is the non-aromatic compound. So resonance energy will be greater in case of aromatic. And if we talk about these two questions, this compare the resonance energy, this and this. So first, because it is aromatic, this is second because it is non-aromatic, third it is anti-aromatic. Now second point, number of electron delocalized. If both are aromatic, then how do we compare? Like this and these two, how do we compare? Because the number of electron delocalized is more in case of second, so that is more. Now if we talk about this compound, so number of electron delocalized, first both are non-aromatic, both are aromatic, but number of electron delocalized is more here, so it is no. So number of atoms participating in the resonance, number of atoms participating in resonance equals to resonance energy. That will be equals to resonance energy. Third, CH3 C double bond O negative, CH2 C double bond OH. So here, if we say that first one is equally contributing and second one is, this is equally, what is equally contributing, that we have seen in the types of resonating structure, because both are the equal structure, and this is CH2 double bond C O negative H, that is unequally contributing, unequally contributing it will be, right? So energy of equally contributing will be greater than unequally contributing. Like if we talk about some questions, compare resonance energy. So first of all we have a benzene and we have a pyrrole. Second we have O S double bond O double bond O negative, S double bond O negative. Third we have Cl double bond O double bond O double bond O negative, Cl double bond O double bond O negative. Fourth we have P double bond O negative O negative O negative, P double bond O negative O negative. And fifth we have furane and this structure. Seventh we have pyridine and again pyrrole. Now you have to compare the resonance energy between them. So let's first has equally contributing, unequally contributing. More number of atoms participating in second. In third also more number of atoms are participating. Fourth also. Fifth it is aromatic and non-aromatic. This is aromatic, this is anti-aromatic. Sixth it will be equally contributing, it will be unequally contributing. Both are aromatic, but we were talking about an identical resonating structure. Identical RS, that will be unidentical RS. So these are the basis of the third point we have seen. Now jumps to the fourth point of comparing the resonance energy. We have cross conjugation and extended conjugation. So we have here cross conjugation. This is cross conjugation. How it is cross conjugation we have seen already. And this is extended conjugation. This is cross conjugation, extended conjugation. So cross conjugation, extended resonance energy is greater than cross resonance energy. So extended conjugation is greater than cross conjugation. Like we have seen the more example, if you see NH, this is the extended conjugation, cross conjugation. Here this is the extended conjugation, this is cross conjugation, and the second one is extended conjugation. Some more example of cross and extended conjugation. Let's see what could be the more possible examples of. This is cross conjugation, this is extended conjugation. This is extended conjugation, this is cross conjugation. Now we talk about next point, the fifth comparison, that is overlapping. Overlapping means CH2 double bond CH Cl, and here CH2 double bond CH Br. So if resonance is happening over here, this is forming CH2 negative CH double bond Cl plus, and CH2 negative CH double bond Br plus. So overlapping here will be 2p pi and 3p pi. 3p pi chlorine orbital, 2p pi is carbon orbital. Here 2p pi and 4p pi. 2p pi carbon, 4p pi bromine. Now, so which has the less energy difference will be having more resonance energy. Like we have phenol and thiophenol, SH. So phenol having more resonance energy. We have fluorochlorobromide, bromo and iodine. So obviously chlorine has more than bromine than iodine. We have again oxygen, sulfur. So sulfur has more resonance energy. Sixth, we have electronegativity. The sixth comparison consists of electronegativity. So CH2 double bond CHOH. This is the resonance with CH2 negative CH double bond OH plus. But when we have CH2 double bond CH and H2, it will be forming resonance with CH2 negative double bond CH2 single bond CH double bond NH positive NH2 positive. So electronegativity, we know that FONCl, this is the order of electronegativity. So oxygen has more electronegativity than nitrogen. So nitrogen can easily donate and it can easily accommodate the the positive charge as compared to oxygen. So the order will be nitrogen. This will be having more resonance energy. Next we have CH2 double bond CH and CH2 negative. We have CH2 double bond CHO negative. We have CH2 double bond CH NH negative. So in this case we can understand first this will be and second this will be and third the least stable will be the oxygen. Here the first will be highest stable. If we talk about the resonance energy of CH2 CH and CH3, CH2 double bond CHOH, CH2 double bond CH NH2. So when these will break, it will break like this. So the energy, resonance energy will be 1, then 2, then here will be 3. That will be the order we will be seeing. Now let's compare some more on the basis of what we have studied over there. Question: compare resonance energy. First of all, we have phenol OS, then we have aniline, then we have chlorobenzene. Here the 1, then 2, then it will be 3. Because again NH2 order FON and Cl. But here chlorine has 2p and 3p overlapping. Instead nitrogen has 2p and 2p overlapping. So electronegativity of nitrogen and chlorine are approximately same, but the overlapping dominates over NH2. So extent of resonance or quality of resonance increases. So first of all we have nitrogen, then we have oxygen, again oxygen and chlorine. So electronegativity was the second rule. First was we have to go through the order. First was or aromatic, second was number of atom participating, and third was equally contributing, unequally. Fourth was cross conjugation, and fifth was overlapping. Sixth was electronegativity. So first of all we will be comparing the overlapping good in 1 and 2. Here also 2p and 2p, but electronegativity, the next point that dominates in second case. So that's how we compare. If we compare line wise, like we have seen in resonance, stability of resonance, NH. So second case is more stable, oxygen and nitrogen. We have oxygen and we have sulfur. The overlapping and better in case of oxygen. We have CH3 C double bond O negative. We have CH3 C double bond O acetic acid. So in first case it is identical resonating structure, and second case we don't have the identical resonating structure. Seventh one is Fry's rule. That is quite important. Sometimes question arises, what is the Fry's rule? So seventh one is Fry's rule. So according to Fry's rule, we have anthracene, and one we have phenanthrene. Phenanthrene. It has 2 benzenoid form. It has 3 benzenoid form. What is benzenoid form? The number of rings that looks exactly like benzene. This looks like benzene, and these three bonds. This look like benzene, and yes, this doesn't look like. So first look like, second look like, but third doesn't. So it has two benzenoid form. This look like benzene. 1, 2, 3. The double bond, if it is here or here, it is same, right? And it doesn't look like benzene. And this, it has three benzenoid form. So more number of benzenoid form, resonance energy is directly proportional to number of benzenoid form in multiple benzene ring. Like like we have some other examples, like we have naphthalene, and we have biphenyl. This is naphthalene, and this is biphenyl. In naphthalene, we have other possible structure is other possible structure is 1, 2, 3, and this. So, but in biphenyl, these all always remains the two benzenoid form. Benzenoid form. But in naphthalene, yes, first one is benzenoid form, two benzenoid form, but this is only have one benzenoid form. It has two benzenoid form. So it is less than the biphenyl. So biphenyl would have more resonance energy. Now we compare anthracene, and then biphenyl, triphenyl. So again, anthracene could have all these. It has two benzenoid form, and it has three benzenoid form always, right? So obviously the triphenyl system, the triphenyl ring is having more resonance energy as compared to benzene than anthracene.